Hello everyone. Here we're going to study this chapter, chapter 6. The topic is bending, or we call it bending moment. Inside this chapter, the introduction of these slides would like to show 5 important topics in these contents. The first one is shear and moment diagram, which are very similar to what we have learned in chapter 4 and 5. In chapter 4, we learn actual load diagram, and chapter 5, we learn torque diagram. Okay. For shear and moment diagrams, they have very similar function as these two types of diagram. They both used to find the maximum and minimum shear force and moment along the beam. Okay. So based on this statement, we know that the distribution of shear force and moment along the beam, may have different amounts of shear force and moment point by point. So we need to find the maximum value of them, and then you may have chance to calculate the maximum shear stress and maximum bending stress inside the beam. So next one. After we know the maximum shear force and maximum moment, a special moment in this chapter, we need to use these internal moment, okay, to derive the corresponding bending stress. Note that bending stress is the so-called normal stress. After we learn the basic skill to derive the bending stress, in section or topic C, D, E, we'd like to find some special skill to solve some special geometry, some special material composition. For section C, the main consideration is symmetric cross-section. For cross-section, if you have symmetry with respect to the vertical axis, which means your right portion and left portion are symmetric, okay, then you can use the skill described in this section to solve their bending stress. Next one, if you have some more complex geometry like unsymmetric, okay, cross-section, just like this one, unsymmetric one, okay, then you can use these topics to solve them, the skill in these topics to solve them. The final one is to consider if you don't have homogeneous material, we call it inhomogeneous material, or directly call it composite material, then we need some new skill, okay, some other skill to solve these types of problem and derive the stress inside these types of beam. Okay, so composite material or inhomogeneous material will be solved in this section. So that's all the important topics we'd like to discuss or to learn in the following contents. Here's the section 6.1, the first section of this chapter. We'd like to learn shear and moment diagrams. Before we go to the detail, we we'd like to introduce 3 basic beam structure, beam style. First of all is called simply supported beam. We call 剪支梁 in Chinese. This type of design have one pin support on the left side or on one side, and a roller contact on the other side. So in this geometry, you usually have 2 constraints on the pin support and a single constraint in vertical direction on your roller support. For the second geometry, we call it cantilever beam. In this structure, one side of beam is free, the other side of beam is totally fixed. So on the totally fixed side, your boundary condition would be would have three constraints such as the force or the displacement in the horizontal direction, in the vertical direction, and the constraint of the slope or the bending uh, at the end. So we have three constraints on one side and no constraint on the other side. That's what we call it cantilever beam. 悬臂梁 is the Chinese name of this beam. The final one would be overhanging beam. We may call it 外升梁 or 外延伸梁. Okay. The boundary condition of this beam is very similar to simply supported beam. The only difference is this part. Okay, we have one extension portion at the end of one side of the beam. Okay, so this is so-called 外延伸. Okay, due to this portion, due to this part. The remaining part of the support or boundary condition is exactly the same as simply supported beam. All right. Then after we introduce the beam structure or the type of the beam in previous slides, next one in this slides we'd like to go to the applied load types and the sign convention. For a beam like this, usually we have various types of applied load, external applied load, such as distributed load, bending moment, and point load or point force. And we may have different number of these applied loads and different types of combination. So in general, you may have various or numerous types of loading condition on the beam. So that is the challenge of our homework and our exam problems. But no matter how many types of applied loads, we can try to classify them into these three basic loading conditions. Distributed load is just like this one. Bending moment, we present this moment as this symbol. Okay, counterclockwise arrow or clockwise arrow. For point load, it's just like an arrow point upward or downward. Okay, that is all the external applied load types for beam structure or bending and following chapter shear force chapter. Next one, we'd like to know how to examine or how to present our internal force. We call it shear force, moment, and external distributed load. This is the sign convention for them. For external distributed load, upward direction is the positive direction. Okay. For internal shear force, depending on the side or the direction of your cross-section. For this one, this is kind of the so-called right cross-section. You have downward direction as your positive direction. For the other side, left cross-section or left-hand side cross-section, the upward direction is the positive one. So for any cross-section, when you see the internal shear force or the following internal moment, the positive direction is very important or very critical for you to decide the sign in your diagram, in your calculation. Okay, so this is the definition for positive internal moment. Okay, that's all the definition for beam in under bending under shear force. And for internal force and moment, the internal force and moment are different point by point along the axis of the beam. Okay, so this is very common on your applied loads and also in your internal force distribution, moment distribution. Therefore, shear and moment diagram are needed to find the maximum value. Of course, that also means that the shear and moment diagram should be much more complex than all the other diagrams. All right. Here's the way we try to plot some complex shear and moment diagram. The method is called method of section or section method. Why we need this method? The reason is here. Due to discontinuous forms of the shear and moment function. Okay, discontinuous. Why we say this word over here? The reason is like this. If you have a simply supported moment or concentrated moment at C, at D, or just like this, your distributed load start from here to B and then disappear suddenly at this point. So these kind of condition, like the condition at B, C, and D, are all belong to discontinuous form. Then, in order to present this kind of condition in your diagram very well, you need to plot them section by section. So it means here, in order to plot the diagram for this beam, this is not a very complex beam, but from A to B, you need one coordinate system to present the distribution within this section. And then between this continuous point and the other discontinuous point, you need another coordinate system x2. The final one, C to D, you need the third coordinate system. That is the way we call it section method. We divide our beam into several different sections and add or assign corresponding coordinate systems for them. One section, one coordinate system. Two, you need two coordinate system. And of course, you need four, you will have four, okay? Here's an example to show how to derive or how to plot our shear diagram and moment diagram together. Here is the first example. We have a simply supported beam. This is the structure-wise. For the loading-wise, you have a uniform distributed load W. Then next one, using free body diagram of the beam, the total beam, we get the reaction force on both sides. This coming mainly from their boundary condition. After that, we try to cut the middle of this beam with a length of x, just like this one. This is a partial free body diagram of the beam at one side, at the left-hand side. Okay, so point A is here. The supported force or reaction force here is given as WL over 2. And then the upper distributed load get a resultant force Wx in the middle of the beam. Then you'd like to use these two reaction force and moments along the cross section. Notice that the given force and moment should follow the sign convention as a positive sign for each case. So this is the positive V and positive M for both cases. After that, based on this function, this relation, we get one formula for shear, one formula for moment. All right. So this is coming from force balance, this is coming from moment balance. After that, you can plot the diagram by this function for shear, this function for moment. And it is quite interesting that this is a linear form because you only have x with first order. So that is reason you start from WL over 2 and gradually decrease to 0 in the middle and to the minus WL over 2 on the other side. And for the moment wise, it's coming from starting from 0 and then to the maximum in the at the middle and then decrease to 0 again on the other side. For the maximum value, you can input L over 2 into the moment function and get the maximum value as WL squared over 8. as your maximum value in your diagram. That's all the process you need for this example. Here's the second example. You get a cantilever beam with a linearly increased distributed load from the initial point to the end. Okay, the maximum point is here. The total length is L. After that, you know, this kind of boundary condition give you this free body diagram with two reactions on the fixed end. The horizontal force is 0, so we just neglect that part. Otherwise, we should have 3 for fixed wall or fixed boundary condition. Okay. Next one, the resultant force of the distributed load is located at here. 2 over 3 times L is the location of the resultant force. After that, we try to cut partial of these beam with the with the length of x. Okay, this is on your left hand side portion. You get a portion of the beam. We call it free body of a part. Of course, on your left hand side, the reaction force and moment is here. The resultant force of the linear distributed load is here. The total magnitude is given at this place. The location from this point to the other end is 1/3 of x. And then, similar to the previous one, the free body diagram along the cross section should have internal force and moment with a positive sign for both cases. After that, you derive your shear function and moment function for each case by this free body diagram. Once you get two equations, you can use them to plot the shear diagram on the upper side, upper part, and your moment diagram at the lower part. This is the third case. We have a simply supported beam with a central load or concentrated load at B in the middle. All right. So for this case, we still follow the same process. Free body diagram of the beam, total beam. All right. You get the reaction force at C and B. A and C. After that, because in this case we have a discontinuous form due to the point force at B, we need to use a so-called section method in the section AB and BC. So this is the portion. This is the free body diagram in section AB. Starting from A to distance x1. Okay, this is the first coordinate system. And for the section between BC, we get this free body diagram. And of course, we give V1 and M1 for first coordinate system, and we use V2 and N2 for the second coordinate system. After we derive the corresponding functions, shear function and the moment function for each case, we can plot the shear distribution, shear force distribution, and moment distribution in the first section based on M1 and V1, and use the V2 and M2 to derive the shear force and moment diagram in section BC. That's all the process we need for these two sections. Here's the fourth case and the final case for this section. Example 4 shows similar geometry, simply support beam, and we put a concentrated or a single moment at B. After we assign this homework or the topics for you, you can use the same process. Free body diagram for the whole beam, and the reaction at A and C are given here. After that, follow the section method mentioned in the previous slides. we cut the middle between A and B, get these free body diagram, and we cut B and C, the point at the middle of BC, and get the second free body diagram. For both cases, we derive V1 and M1 function for the first section, and V2 and M2 for the second section. After that, we plot all of them and get the whole shear diagram and moment diagram for these problem. Okay.